All right, a lot of you have already seen videos about the integral test because I posted a link last night. But for those of you who did not see the integral test, or perhaps you want to see it from a slightly different perspective, although pretty close because I picked a video that was close to my perspective, I'm going to take a little bit of a look here at the integral test and how it works. And before I start this, this is an idea that we'll look at more when we look at the comparison test. But one of the really important ideas with the integral test is the idea of a series being bounded, okay? In other words, if I have a series that I know, let's say I plot points for a series, and I know that the terms in this particular series converge. If I have a series that has individual terms that are less than or equal to the terms in that series, then that series will also converge, okay? We basically say that this lower series here is bounded by that upper series, okay? That's a pretty important idea, okay? But again, each of the terms would have to be less than or equal to the terms in the original series that I knew converged, okay? If this series diverged, if I had terms that were less than that, just because these diverge doesn't necessarily mean that a series with terms that are smaller will also diverge. If the series diverges, the only thing you know is that a series that has terms that are bigger than the terms of a divergent series would also diverge, okay? So basically, if you're going to show that a series converges, the terms need to be less than or equal to the terms of a series that converges, okay? We would say that series is bounded above by some other series. Meanwhile, if you have a series that you're trying to show is diverging, you need to show that its terms are greater than or equal to the terms of a divergent series. We would say that it is bounded below by a divergent series, and so that series diverges, okay? So that's kind of what's going on in the background of what I'm going to be talking about today. All right, so here's the big idea. Let's say I've got a series like the sum from 1 to infinity of 1 over n squared, okay? And I want to decide, is this series convergent or divergent, all right? Now, you may want to list out a couple of terms, okay? So when n is equal to 1, this is equal to 1. When n is equal to 2, this is equal to 1/4. When n is equal to 3, it's equal to 1/9, and so on, okay? Anytime you're doing a series problem, you need to have that list of series tests that I gave you in your head. You need to be kind of going down that list and asking yourself, is it this, is it this, is it this? It's a little bit like factoring for me too. You've got different factoring processes. You try to kind of put a list. Same kind of thing here, okay? The first thing you always need to check is the nth term test, okay? Remember, the nth term test doesn't tell you if a series converges, only tells you if it diverges. But the terms have to be decreasing to 0. Okay, if the terms aren't decreasing to 0, then it's not possible. If I'm adding, 1 plus 1 plus 1 plus 1 plus 1, and the series never converges in the individual terms down to 0, it's not going to have a sum. Okay, so technically you take the limit as n approaches infinity of your expression. Okay, 1 over n squared is going to approach 0 as n approaches infinity. So the individual terms here approaching 0, that means that this could converge. Doesn't mean it does. It just means I can start looking at other tests, okay? So then we can look at other things we've discussed. Is it geometric? And I think if you check the multipliers here each time, you're not multiplying by the same thing each time. This is not a geometric series, okay? Is it harmonic? It looks a little bit like a harmonic, except the terms are being squared. It's not a harmonic, okay? It's not a product of a harmonic or anything like that as well. So at this point, we really don't know what to do, okay? And here's where the integral test comes into play. If this series looks similar to a function that you know you can integrate, you might be able to use the integral test, okay? In this case, I could make a comparison to the function f of x equals 1 over x squared, okay? Now, this is a continuous function. It's got infinitely many points, and it's continuous. This is not a continuous function, it just has individual points if you were to graph it, okay? So we're comparing this series to a function that has some similarities, okay? That's really the big idea. All right, so here's the visual, okay? If you graphed this series, it would have an asymptote at 0. It would be doing this sort of thing, okay? What you can do is you can match up individual points from the sequence. Again, this is not defined for fractional values, for example. This is, okay? So the sequence is essentially just going to be points on the function curve. This is function f of x, 1 over x squared, okay? And so, for example, at 1, the function value is equal to 1. I'm just going to write a 1 there. At 2, the function is equal to, not 2, the function is equal to 1/4, the second term, okay? At 3, the function is equal to 1/9. And you can see it's dropping off really rapidly. It kind of implies, you know, maybe this will have some kind of a sum. Here's the concept of the integral test. What you're really going to do is you're going to represent your series using areas, okay? You're going to create rectangles that basically have a width of 1 and a height that's the functional value, okay? So, for example, I can create this rectangle here, okay? That rectangle has an area of 1, okay? And that's my first term, okay? This is a left-hand sum, if you're thinking about Riemann sums. This rectangle here, not drawing this very well, but this rectangle here is a 1 by 1/4, not drawn to scale, but it has an area of 1/4, okay, that's that. We can draw another rectangle here from 3, it goes like that. It's got a height of 1/9, it's got a width of 1. And so the area of this, all the way out to infinity is going to end up being my series, okay? Here's the key. Notice each of these rectangles is greater than or equal to the actual area under the curve, okay? What I can actually do is I can check and see, does that integral converge? If I take the integral of this function from 1 out to infinity, does that integral converge, okay? Or does it diverge, okay? If the integral diverges, my series terms are all greater than or equal to the original function that I'm comparing it to. And so if the function integral would diverge, in other words, if the area under that is infinite, then certainly when I add up these terms, they're going to be infinite because they're going above the curve, all right? So let's take a look here and let's see what happens. So I'm going to take the integral of the related function, okay? I'm going to take the integral of 1 over x squared dx, okay? It's going to be the integral between, we're starting at 1 and we're going to infinity, okay? These will be improper integrals, all right? And what you're going to find out when you integrate this, let's see, the integral here, that's x to the -2, right? Okay, so raise the power by 1, divide by the new power. You're going to get negative x to the -1, which is -1 over x, okay? And if you remember, you're really taking the limit of this. We're evaluating it between 1 and infinity. I'm going to say we're evaluating it between 1 and b because infinity is not a number. And so I can take the limit of this as b approaches infinity, apply the fundamental theorem here. That's going to be -1 over b minus -1 over 1. Okay, and now we can apply this limit as b approaches infinity here. You'll see this whole term here as b approaches infinity, -1 over infinity approaches 0. Okay, and so this whole thing is going to approach 1. Okay, what this says is the area under this curve approaches a sum of 1. Okay, be careful. That does not tell you that the series is approaching 1. Okay, because notice the terms of the series are poking out above that curve. Okay, now here's the other problem, and this is significant. I didn't prove that the series converges exactly. Okay, what I proved is that a series, that a function that is less than the terms of this series converges. Well, each of these terms are a little bit bigger than the terms of the function that I compared to, which means I haven't really exactly proved that the series is convergent yet, okay? I just proved that a related function is convergent, and it seems a little bit more plausible, okay? So technically, technically, here's what's going to happen. What you can do is you can go back and you can look at that related function again, okay? And you can basically do the lower sums, okay? So this is still f of x equals 1 over x squared, okay? It's that related function, okay? And I'm still looking at values at 1 and 2 and 3 and so on, okay? What you're going to do here is you're going to look at the lower terms. You're going to start this out at 2, okay? And so if you start the series at 2, you could say, okay, that would give me 1 over 2 squared, that's 1/4, okay, that has an area of a fourth. Then we can go to 3, and again, we're doing the rectangles under the curve, so that's 1/9, okay? And then we can go to the next one here, that's gonna be 1/16, and so on, okay? I've already shown that integral converges, all right? So as a result, we now have terms that are less than the terms of a convergent series, okay? Which means that this series is going to converge. Well, you look at that and you say, well, yeah, but that doesn't include the fact that n equals 1. Well, that's just adding one other number on, okay? We know what the functional value at 1 is. If I have a series that's convergent for term number 2 through the infinite term, I can always add on the first term at the start, and that's a set value. We know what that is. It's still going to be convergent because that first value is not infinity. Okay, so what we basically walk away from is this: that the integral test is actually really easy to use. The integral test just basically says, and again, you need to start out with a series that has a function that's related that you know you can integrate. If you can't integrate it, it's not a good test to use. But if you can integrate the function, turns out if the related function, and again, that function needs to be a decreasing continuous function. Technically, it's called a monotonic function. It's always decreasing. But if the function is positive, decreasing, monotonic, you should be able to take the integral. If the integral from 1 to infinity or 2 to infinity, whatever your starting term to infinity is, if that integral converges, the series converges. If the integral diverges, the series diverges. Again, you will not be able to find the sum of the series. You'll just be able to tell if it converges or diverges. And that, again, is because you can see when I'm representing the series using areas of rectangles, they're always going to be a little bit above the curve or a little bit below the curve. So you could probably say that the series is bounded by a certain value. You know, the sum is going to be no greater than a certain value or no less than a certain value, depending on what it's doing. But again, you're not going to actually find sums. Geometric series and telescoping series are really going to be the main cases where you may actually be able to find a sum. It's actually pretty rare at this level of calculus.